In this video, I'm going to talk about capacitors in series and capacitors are in parallel. So here, capacitors in series, capacitors are in parallel. I will also compare what happens if resistors are in series and resistors are in parallel. Now, we know that if it is in series, at any node, only two elements exist. So if you look at here, I have three nodes. Node is nothing but a junction where two or more elements connected together. So here I have three elements. So at node 1, capacitor and voltage source connected. At node 2, capacitor 1 and capacitor 2 connected. Node 3, capacitor 2 and voltage source connected. When it comes to parallel, both elements, both capacitors, start at the same node, okay, and their ending point is also another same node. That is called parallel combination. Okay, here this is also connected to source V. Now, when capacitors are in series, same charge appear on each capacitor. So if capacitor here, charge 1, Q1, charge 2, Q2 is also same as Q. So Q total is same as Q1 plus Q1 equal to Q2. So charge is same. Whereas parallel capacitor, voltage is same. So if I give the supply voltage as V volt, V is same as V1, same as V2. Whereas in resistors, we know that if resistors are in series, the current is same in both resistors. So same current, I total equal to I1 equal to I2. Whereas resistors are in parallel, voltage is same. When the resistors are in parallel, voltage is same. V total equal to V1 equal to V2. I just want to compare resistors with capacitors so you know the difference. And you will see at the end, you will see big difference. Now, capacitors in series, voltage division takes place. Okay, so V total equal to V1 plus V2. So whatever we are giving supply voltage V total, it's divided across capacitor 1, across capacitor 2. Same thing happened when the resistors are in series, V total equal to V1 plus V2. Whereas parallel capacitor, charge division takes place. So if this is supplying total Q total, Q1 is going to appear across C1 and Q2 is going to appear across C2. So Q total equal to Q1 plus Q2. Same thing happen in parallel resistor, but instead of Q, we call this as current. Current is going to divide. Is it going to divide equally? No, it's going to divide based on the resistance value. We already know current division rule. So based on that, you can find the current in across each resistor, or current passing through each resistor. Now, when it comes to the Q total or total capacitance, say we already know Q equal to C times V. So based on this, I can write V equal to Q over C. Q is the charge on each capacitor, C is the capacitance value, V is the voltage across the capacitor. Now V total equal to Q total over C total equal to V1 is nothing but Q1 over C1 plus V2 is nothing but Q2 over C2. So based on this, this is our equation. Now we know that in series, Q total is same as Q1, same as Q2. So if I substitute Q total equal to, this is also Q total, this is also Q total, they cancel out each other. 1 over C total equal to 1 over C1 plus 1 over C2. So when the capacitors are in series, instead of direct addition, you're going to do 1 over C total equal to 1 over C1 plus 1 over C2. Now when I simplify this, basically C total equal to C1 times C2 over C1 plus C2. This is our total capacitance value. Now, okay, when they are in, that is when they are in series. So in series, this formula is similar to the parallel resistors formula. Okay. Now, when they are in parallel, okay, Q total is nothing but Q1 plus Q2. So Q is nothing but C1 V total equal to, C total times V total equal to C1 V1 plus C2 V2. When they're in parallel, V is same. V is same as V1 V2. So they get cancel out each other. C total equal to C1 plus C2. So when they're in parallel, I'm going to use this formula. So I want to compare resistors with capacitors because when the resistors are in series, it is R1 plus R2. When capacitors are in parallel, C total equals C1 plus C2. That's the difference I want you to see. Okay. So other than that, remaining everything is same charge across the capacitor, same current in resistors, voltage division takes place in capacitors, same thing, voltage division takes place in resistors. Okay. Now, so we understand the capacitors when they are in series and parallel. So here is an example. In this example, he's asking about find the total capacitance value. So here, it's look like a ladder circuit similar to the resistors. In ladder circuit, we always start the capacitor which is far away from the open terminals or from the source. So here I'm going to start from the 6 microfarad capacitor. See if the 6 microfarad capacitor is in series with something or parallel with something. I can clearly see these two are in series because at this node only those two elements exist. So the total is going to be, since they are in series, you have to use the parallel formula, which is 3 times 6 divided by 9, or 3 plus 6. 3 times 6 divided by 3 plus 6. That will give you 2 microfarad. Okay. So now that 2 microfarad is in parallel with 4 microfarad. So here I have 4 microfarad and 2 microfarad. So these two are in parallel. Now when they're in parallel, it's just direct addition. 4 plus 2, which is 6 microfarad. Now I'm going to redraw the circuit again. So I have 12 microfarad and 6 microfarad. So everything else, I already found the equivalent value, which is 6 microfarad. And this is 1 microfarad. Now I can see these two are in series. 6 and 6 are in series. I end up with 3 microfarad. Now 3 microfarad is in parallel with 1 micro. So when they're in parallel, the total is going to be 4 microfarad. Okay. So this is point A and point B. So basically I'm taking this as point A, point B. So the open terminals, I'm labeling them as A and B. Okay. Now here, okay, C total equal to 3 microfarad. Sorry, how do you get the 3 microfarad? So 12 microfarad and 4 microfarad, they are in series. So the result is going to be C total equal to 3 microfarad. Okay, I'll stop this video here. In the next video, I'm going to solve a couple of examples based on the capacitance value. Thank you.